Today we're on pages 116 and 117, solving exponential equations using logarithms. You want to have your calculator and a highlighter. When solving an exponential equation algebraically, it needs to be rewritten in log form. Solve 4 to the x equals 8 using logarithm. This is our exponential form. We're solving for x, which is the exponent. So we write it in log form. Remember, in log form, we spell out log base, where s is for equals. So log base 4 of 8 equals x. We have x by itself. We go to our calculator, alpha window number 5. Log base 4 of 8 is 1.5. Math frac that. Just prefer the fraction. So x equals 3 over 2, or 1/2. Exercise 2, solve each of the following equations for the value of x. Round your answers to the nearest hundredth. You must isolate the base and exponent before switching to log form. Very, very, very important. Here we have our base and exponent. They're already isolated, so we simply switch to log form. Log base 5 of 18 equals our exponent x. Calculator, alpha window number 5. 5 of 18, and we're rounding to the nearest hundredth. 1.7958 is going to, let me write this down, 1.7958, there's more to that. The hundredths place is the 9. We look to the right, 5 or greater, that rounds up, so 1.80. B, here's our variable x. With our base, we need to isolate that. We need to get this by itself. I strongly suggest that you circle that. We need that to be isolated before we switch to log form. So subtract 12 from each side. You don't have to show this. 4 to the x equals 100. Now switching to log form. Log base 4 of 100 equals x. Calculator, alpha window number 5. 3.3219. Rounds to 3.32. Again, our base and exponent need to be by themselves. So please circle 2 to the x. Has to be by itself. So our first thing we do here is we divide by 5. 2 to the x equals, I think that's 312. So, and now switching to log form. This is our base, that's our exponent, that's our answer. So we spell out log base. Log base 2 of our answer 312 equals the exponent x. And to the calculator. .2854, rounding to nearest hundredth, 8.29. My squiggle equals are approximately. Okay, so they can become more complicated. Solve each of the following equations for x, round answers to the nearest hundredth. And 6 to the x plus 3 equals 50. All right, so our base and exponent are isolated right here. We switch to log form. We have log base 6 of 50 equals x plus 3. Now, we can key this into the calculator. I hold off. I'm not going to touch the calculator until I have x by itself. So the next step is to subtract 3, and I have log base 6 of 50, subtract 3 equals x. Now I'll put that into the calculator. Make sure that when you key it in, that you arrow out of the log parenthesis, right? Arrow out of log base 650, and then put the subtract 3. If you have the subtraction of 3 within the parentheses, it's incorrect. So x equals approximately negative 0.8166, rounding to nearest hundred, negative 0.82. And number 6. Okay, so the base and exponent, that's a much more complicated exponent, but that's okay. Base and exponent are isolated, so we switch to log form. Log base 1.03 of 2 equals x divided by 2 minus 5. We want to get x by itself. We add 5. I think I'll keep this in parentheses, because this log right here, log base 1.03 of 2, that stays together. The plus 5 is outside the log. This equals x divided by 2. And now we would multiply both sides by 2. Now be careful here. Right, the whole thing on this side is multiplied by 2. So this would be 2 times parentheses log base 1.03 of 2 plus 5 equals x. Now going to the calculator, 2 parentheses alpha window number 5. And make sure you're looking at this. Once you key in the base 1.03, right arrow over to get to the argument part of 2. And I'm out of the log, plus 5. And close my parentheses. So x is approximately 56.8995 to nearest hundredth, 56.90. On our next page. So now that we're familiar with this method, we can revisit some of our exponential models from last unit. Recall our exponential functions that are growth and decay. If a quantity, capital A, is known to increase or decrease by a fixed rate r, lowercase r, in decimal form, then capital A can be modeled by, so we have A of t equals A sub 0. This A sub 0 is the same as our lowercase a that we worked with last unit, times 1 plus r to the t for growth, 1 minus r to the t for decay. So where A sub 0 represents the amount of A present at time equals 0. So A sub 0 is the initial value. Again, this is the same as our lowercase a. Same as lowercase a from Unit 3. A biologist is modeling a population of bats on an island. When he first starts observing them, there are 104 bats. 104, that looks like our A sub 0. The biologist believes that the population is growing at a rate of 3% per year. Write an equation for the number of bats, B of t. So instead of A of t, we want B of t equals 104, this is growth, times 1 plus our R value, 3% as a decimal is 0.03 to the t. All right, that's done. Using your equation from A, algebraically determine the number of years it will take for the bat population to reach 200. So an output of 200. Replace B of t with 200. 1 plus 0.03 is simply 1.03. And we need to find t. Okay, so this is where t is our exponent. We want to get our base and exponent by itself and then switch to log form. All right, so we have 104 times that, divide by 104. If this is not a nice decimal, then I might just leave it as a fraction. 200 divided by 104. Math frac that. 25/13. So we have 25/13 is equal to 1.03 to the t. This is our exponential form. Switching to log form, our base is 1.03, so log base 1.03 of 25/13 is equal to our exponent t. And now to the calculator. Alpha window number 5, 1.03. Again, looking at the calculator, arrow out, and I'll just go up and grab that. And arrow out. Rounding to nearest year. So we have t is approximately 22.1229, which is 22 years. Exercise 5, a stock has been declining in price, decreasing at a steady pace of 5% per week. If the stock started at a price of $22.50 per share, determine algebraically the number of weeks it will take for the price to reach $10. So this is the starting amount, A sub 0, and this is our A of t after so many weeks. All right. So A of t is equal to A sub 0 times 1 minus r to the t. And our ending amount, we're looking for $10, when 22.5 was our starting amount. 1 minus 0.05 is our r value. Again, so let's circle this. This is what we need to get by itself. And I strongly suggest that you circle that base and exponent. And we divide by 22.5. Just leave it like that. 10 divided by 22.5 equals 1 minus 0.05 inside parentheses here is equivalent to 0.95, so the t. And switching to log form, just going to check, 10 divided by 22.5 is equal to that. Math frac that. That's 4/9. Log base 0.95 equals t. And putting that into the calculator. Grab that. So t is approximately 15.8096. Each time I'm truncating. Truncating is you're just cutting off after the fourth decimal place. Round the answer to nearest week. So 16 weeks. And number 6, if you like, you can pause the video and try these on your own. We're solving for x to nearest hundredth. Always, always, always get that base and exponent by itself before you switch to log form. Right, so A, I'd add 3. 4 times 2 to the x equals 20. I meant to switch colors, but that's all right. Divide by 4. 2 to the x equals 5. Switch to log form. Log base 2 of 5 equals x. Go to the calculator. To the nearest hundredth. .32. And 17, or rather B. Yeah, we'll divide by 17. So 5 raised to the x divided by 3 equals 4/17. Switch to log form. Log base 5 of 4/17 equals x divided by 3. Getting x by itself, undo division, multiply by 3. And to the calculator. 3 times. Off a window, number 5. 5 is the base, 4/17. Arrow out of that, close the parentheses. Negative 2.6970, nearest hundredths, negative 2.69, no, 70 rather, eraser. Again, remember, all right, before you switch to log form, you have to have your base and exponent by itself. Thank you for your attention.